People pay thousands of dollars for this stone because of the microscopic fragments of raw copper suspended inside it by ancient lava. Most sunstones around the world get their sparkle from common iron minerals like hematite, but the true Oregon Sunstone is a highly calcic Labradorite feldspar fueled entirely by copper. To find its origin, you have to look back 15 to 17 million years ago. The Yellowstone mantle plume tore through the Pacific Northwest, unleashing massive eruptions known as the Columbia River Basalt Group, and leaving behind these towering columns of volcanic rock. As that magma cooled, it slowly crystallized into plagioclase feldspar. The cooling process trapped pure, native copper directly inside the growing crystal lattice. The intense heat of the mantle plume, paired with the specific chemistry of the magma, created a perfectly balanced and highly localized environment. Nowhere else on Earth did native copper integrate into feldspar quite like this. When you look at an Oregon sunstone, the first thing you notice is the metallic glitter. Gemologists call this effect Schiller. Schiller happens when relatively large, flat copper platelets align themselves perfectly parallel to the crystal's natural internal cleavage planes. But if we zoom in exponentially to the submicroscopic level, those plates give way to tiny, elongated nanoparticle spheres. These create intense pleochroism, meaning the stone actually shifts color depending on your viewing angle. The specific color is dictated by the exact size of the particles. When the copper nanoparticles are under 80 nanometers wide, they absorb blue and green light wavelengths, allowing only a rich spinel red to pass directly through to your eye. If those particles grow just a tiny bit larger, around 100 nanometers, they act as a roadblock. They scatter the red and orange light outward, which allows stunning teals and greens to transmit cleanly through the crystal. Every color, every flash, and every dollar of market value comes down to the physical size and alignment of suspended metallic copper. Over millions of years, tectonic shifts and weathering pushed these crystals to the surface of the harsh high desert in southeastern Oregon. Long before commercial mining, indigenous peoples, particularly the northern Paiute, gathered these weathered megacrysts from the earth, trading them across the American West for adornment and ceremonial use. Today, turning those rough stones into faceted gems is an engineering hurdle. The crystal's perfect cleavage planes mean it can easily shatter on the cutting wheel if subjected to mechanical shock. Cutters solve this by mathematically mapping the stone before the blade ever touches it. They intentionally offset their bottom facets by exactly 7 to 10 degrees from the internal cleavage plane. Then there's the issue of light. Because the stone has a relatively low refractive index, light passing through it naturally wants to leak out the back. Lapidaries cut a strict 44 to 45 degree pavilion angle at the bottom to force the light to bounce back up to the viewer. Transforming a piece of rough sunstone into a finished, high-performance gemstone requires master-level lapidary math to overcome a highly complex biaxial structure. In the early 2000s, the market was suddenly flooded with cheap, red stones marketed as andesine. Traders were artificially diffusing copper into pale, low-quality feldspar and selling it at a premium. To separate the natural volcanic stones from the lab-treated counterfeits, gemologists turned to ultraviolet fluorescence testing. The artificial treatment leaves a distinct chemical signature. In the lab-treated stones, the injected copper exists as charged ions, which glow aggressively under UV light. But in a natural Oregon sunstone, the native copper is purely metallic, zero-valent copper. Under a UV lamp, the natural stone stays completely dark. That atomic-level reaction provides an absolute fingerprint, allowing scientists to permanently weed out fakes and protect the integrity of the natural gemstone market. That scientific defense quickly translated into a market defense, leading miners to form the Oregon Sunstone Miners Association. While global gem supply chains are often opaque and exploitative, Oregon sunstones are pulled from the ground by small, family-run desert operations, enforcing strict environmental and labor standards. You are looking at a frozen snapshot of a volcanic cataclysm. It is a marvel of optical physics, wrapped in centuries of cultural history. It is a rare convergence of geology, ethics, and physics, occurring in a single remote corner of the Earth, making the authentic Oregon sunstone genuinely irreplaceable.